Welcome back, everyone. Take a second to pat yourselves on the back. You've totally nailed static schedules, verified those read-write sets, and built some really solid dependency graphs. You've proven you know exactly how to group parallel safe transactions on paper. But today, in this explainer, we're making the leap from theory to the messy reality of live execution. We're taking that static scheduler output and throwing it right into the unpredictable wilderness of the runtime thread.
Okay, let's dive right into this because, well, this is where the rubber truly meets the road. We're shifting from asking, hey, can these transactions run together in theory, to the absolute chaos of actual parallel transaction processing. Even the most perfectly collapsed dependency graph has to somehow survive real, concurrent worker tasks modifying live state. Let's see how we actually pull that off.
Here's our blueprint for today. 1. The reality of live execution. 2. Speculative execution and state. 3. Catching overlaps with versioning. 4. The abort and retry loop. And 5. Building the runtime harness.
Section 1. The reality of live execution.
There's this beautiful, almost tragic contrast here, you know? On one side, you've got your static schedules. You did the math, compared the read and write sets, and mapped out a graph predicting total safety. It's pristine. But on the other side, runtime reality. Speculative execution creates these interleavings that your static schedule thought were safe, but runtime checks are absolutely mandatory. Why? Because actual state changes bring hidden overlaps, stuff like unexpected data payloads or conditional branches that only show up when the operations are actually running concurrently inside a worker thread. A totally perfect on-paper schedule can literally be ruined by the unpredictability of live execution. If a transaction branches differently based on live data it just read, suddenly your pre-computed read-write set is entirely out the window.
Section 2. Speculative execution and state. Now, what's really fascinating about speculative execution is how we just boldly move forward assuming everything is safe. It basically means we don't wait around. We run operations concurrently just because the static schedule gives us the green light. But, and this is a massive but, it is entirely subject to runtime validation. We're executing with pure optimism, but we're verifying with extreme prejudice. We let the compute happen, for sure, but we don't finalize a single thing until we are absolutely certain the ground hasn't shifted beneath our feet.
And because we're acting speculatively, we absolutely cannot just overwrite live canonical data immediately. That is a one-way ticket to state corruption. Instead, we use a provisional state. Think of it like a temporary holding area, a staging ground for state changes. The transaction executes, computes the new data, and then just parks it in this provisional holding zone. It stays isolated there, completely invisible to the rest of the system, until we are 100% positive there are no concurrent conflicts.
Section 3. Catching overlaps with versioning. So the crucial point here is lightweight state versioning. This acts as our real-time conflict detector. To make this work, you attach a version number, specifically a U64 epoch, to every single state slot in your store. At runtime, as your transaction does its thing, you track its specific read and write sets. Then precisely at commit time, you check those versions. If the version of the data you read speculatively doesn't match the version currently in the live state, you know another transaction snuck in and modified it. It is a simple, elegant, and super effective tripwire. Plus, because we're just comparing 64-bit integers, this versioning mechanism is incredibly cheap computationally. You get robust safety without bottlenecking the entire system's throughput. A real win-win.
Section 4. The abort and retry loop.
This 4-step linear flow is exactly what prevents state corruption and automatically corrects overlaps on the fly. Step 1. The commit time chat flags a version mismatch. Bam! We have a conflict. Step 2. We immediately abort the transaction. That provisional state we were just talking about, we just throw it away. No harm done to the live state. Step 3. We implement a backoff. This is absolutely vital to avoid a thundering herd scenario. We definitely don't want all our threads just instantly slamming into each other again in this vicious cycle of failures. And finally, step 4. We retry the transaction from scratch, pulling the newly updated state. It's just a continuous, self-correcting loop. Section 5. Building the runtime harness. For this harness, we really highly recommend utilizing Rust. We're building a small, local, in-memory state store to test these parallel workers, right? Well, Rust is perfectly suited for this because it gives us highly deterministic execution and exceptionally clear concurrency primitives. It's basically the ideal environment to construct your parallel worker tasks without having to fight language-level race conditions on top of your architectural ones. Let's walk through the exact architecture of the repository scaffold you're going to construct. Your cargo.toml handles the manifest, while main.rs is your entry point to set up those workers. The heavy lifting?
That happens in statestore.rs, which is your in-memory version key value store, and txnwrapper.rs, which provides the runtime instrumentation to track those reads and writes. Finally, you'll have tests/conflictcases.rs, where you'll deliberately write intentional overlapping tests to force conflicts. That's going to output to a structured log we call debugreport.jsonly.
Zooming in on your state store RS file, these are the 3 required API methods you need to build. First, get, which fetches the value and the current U64 version. Second, provisional write, which takes the key, the new value, and the transaction ID and securely holds that data in the provisional state we discussed earlier. And finally, the commit method. This is where the magic happens. This is where your code performs that atomic version check. If the versions match, it moves the provisional data over to live data. If not, it signals an abort.
Let's move on and see how this builds into our logging strategy. As your harness runs, it will output to debug_report.jsonl. It absolutely must use this exact compact logger format. It's line-delimited JSON. Every single read, write, commit, or abort is recorded with its timestamp, transaction ID, key, and version. This format is crucial because it allows your test assertions to inspect the logs programmatically. You'll literally be able to mechanically prove that your harness successfully detected a conflict, aborted, backed off, and retried.
You now have the schematic to build a runtime conflict detector that translates static scheduling into safe, live parallel execution. But I want to leave you with a final thought to chew on as you start coding. This abort and retry loop, it works beautifully in our isolated in-memory harness. But what happens to this delicate balance when transaction scale increases exponentially, like it does on the live C-level runtime? Get your harness built, test it against massive concurrent loads, and hey, let's find out. Happy building!